Thank you for joining us on Synthesis Workshop. My name is Kathleen and I'm part of the new editorial board. On today's Research Spotlight episode, we are joined by Benjamin Groß. He acquired both his bachelor and master degrees at the Technical University Berlin, where he did research in the group of Professor Martin Österreich on Lewis acid catalysis. He also did research at UC Irvine in the group of Professor Christopher van der Wal on the total synthesis of oxidized abiatane diterpenoids. Currently, he is pursuing a PhD at Caltech in the group of Professor Brian Stoltz. And from there, I'll hand it over to you. Thank you for joining us today.
Thank you for the kind introduction. It's my pleasure to be here and to join this episode of the Synthesis Workshop to share our recently completed total synthesis of ineleganolide. Ineleganolide is a natural product which belongs to the larger class of the furanobutylenolide-derived sembranoid and norsembranoid diterpenoids, isolated from various different species of soft coral found in the ocean. Deemed to be produced as a defense mechanism for the coral, these secondary metabolites often exhibit interesting biological activity as cytotoxic or neurotoxic agents. Ineleganolide represents a flagship member of this class, isolated over 2 decades ago by Du and co-workers from the soft coral species Sinularia inelegans. Initially, ineleganolide exhibited cytotoxicity against leukemia cell lines, but further investigations into its biological activity remain unknown. Taking a closer look at the structure, we see a highly rigid and caged framework, further illustrated in the X-ray crystal structure on the right-hand side. In addition, we observe several functional groups and oxidation patterns that represent a key challenge in synthesizing this molecule. These include the central 7-membered ring, a beta-keto tetrahydrofuran moiety, which includes a tertiary ether bridge. This gives rise to a 1,4-diketone. And last but not least, a remote isopropenyl group on the right-hand side of the molecule. These unique and intricate structural features have made ineleganolide a highly sought-after target for total synthesis over the past decades, with only recent success in the last year. I will followingly highlight just a few of these previous efforts. In 2011, the group of Pattenden and co-workers showcased a biomimetic semisynthesis utilizing a macrocyclic precursor derived from the isolated natural product 5-epicyannuleptolide. Upon treatment with lithium hexamethyl disilazane, the precursor undergoes an intramolecular microaddition cascade to give rise to a mixture of products, mechanistically derived from different sites of enolization. As such, they isolated the natural product sinulacmodin C at 10% yield, and its isomer ineleganolide in at 26% yield, with the initial 1,4 addition proceeding from either one of the 2 vicinal carbons to give rise to the 6,7 or 7,6 carbon framework. The Wood group was able to build on this finding and published the total synthesis of sinulacmodin C and ineleganolide only recently in 2022. By elegantly constructing a macrocyclic precursor, they can induce a similar 1,4 addition to give rise to sinulacmodin C in 35% yield, along with its isomer ineleganolide in an 11% yield, constituting the first and only previously successful total synthesis of ineleganolide. In our own group, extensive efforts had been conducted towards the total synthesis of N-ineleganolide, failing at the late stages, however. Having the 7-membered ring and the tetracyclic structure constructed, it proved unsuccessful to isomerize the tetrasubstituted double bond, to then induce an oxamicron reaction to finish the natural product. While this approach did not succeed, there were a couple of key takeaway lessons that paved the way for the future. 1. It is difficult to induce a lot of strain late stage to construct the highly rigid core, hence the unsuccessful oxamicron reaction. And 2. While trying to isomerize the double bond, it was found that the conformation of the central 7-membered ring was increasingly hard to control. This shaped the design of our new route and posed the question, can we construct the 7-membered ring at a late stage? We were drawn to the report from Chris van der Wal and co-workers that made exactly that disconnection. Getting to a late-stage intermediate, they were planning to build the C4-C5 bond through an intramolecular attack of acyl enol ether to a latent oxocarbenium ion. However, their effort got halted due to a conformational issue dealing with a wrong epimer at C12. As shown here, they were unable to epimerize this position to give the correct stereochemistry and then make the final bond. Taking this into consideration, we asked ourselves how we can overcome this problem. This led to the proposal of installing a vinylogous beta-keto ester around the C12 position. Due to the resonance stabilization, we deemed the proton at this position to be increasingly more acidic in the system, allowing for deprotonation to occur. Even if we initially had the wrong configuration at C12, we hoped to readily access the enol form of the intermediate to give rise to a sp2 hybridized carbon at C12. We had then hoped to protonate from the convex face of the molecule to give rise to the correct epimer. With this thought in mind, we started out on our new retrosynthetic analysis of ineleganolide. Tracing back to our previously mentioned enolizable ester, we envisioned disconnecting through a 1,4 addition to construct the C12-C11 bond. Lastly, we would have to construct the C4-C5 bond to build the central 7-membered ring through a potential cross-enolate coupling. However, we were surprised that our precursor actually underwent a 1,4 addition followed by an allyl reaction in the same pot. We could optimize this process, and we were thrilled that this locked in the correct stereochemistry at the crucial C12 position. Leveraging this intermediate, we plan to oxidize at the C5 position, to then set up for a semipinnacle ring expansion to the central 7-membered ring and finish the total synthesis. Our precursor could be disconnected through an esterification of 2 fragments, setting us up for a convergent synthesis. These could be derived from the chiral pool, utilizing linalool and norcorvone as simple building blocks. We first focused on the synthesis of our bicyclic enone fragment. Starting out with the commercially available linalool, we can use a protocol popularized by the Maimoni group to perform a ring-closing metathesis with Hoveda-Grubb's second-generation catalyst, followed by TBS protection of the tertiary alcohol. An allylic oxidation using ruthenium trichloride and slow addition of tert-butyl hydrogen peroxide as oxidant gives us the corresponding enone. Next, we can proceed with conditions developed by our group to alpha-brominate the enone. This whole sequence proved to be very scalable, and I could sneak a picture of the bromination step on one of the pass-throughs. Following, we can do a 1,4 addition of sodium cyanide and subsequent elimination of the bromide to install a nitrile group at the beta position of the enone. Loose reduction of the ketone and protecting the resulting secondary alcohol as the triethylsilyl ether gave us the vinyl nitrile. This can further be reduced to the aldehyde using diisobutyl aluminum hydride. Having initially started out with 120 grams of linalool starting material, we could prepare over 70 grams of the aldehyde in this highly scalable sequence. En route to our bicyclic enone, we envisioned to close the second ring through an intramolecular cyclization onto an alpha-functionalized ketone. Starting from our aldehyde, we could synthesize the ketone, attaching different leaving groups in the alpha position. However, we never observed cyclization even while employing different leaving groups and could not detect the formation of our beta-keto tetrahydrofuran. In looking closer at our compound, we proposed that a successful cyclization would introduce a lot of strain in our molecule as the enone is located in between the 2 rings. In our precursor, we see that the alkene as well as the carbonyl are both sp2 hybridized, resulting in shorter bond lengths. This increases the distance between the tertiary alcohol and the carbon electrophile, making it hard for the alkoxide to cyclize onto the electrophile, kind of like a dog on a leash. We asked ourselves if we could instead cyclize on a beta-functionalized alcohol. Since the carbon-oxygen bond is sp3 hybridized, the bond length is increased, potentially bringing our tertiary alcohol into closer proximity to our carbon electrophile. Additionally, we would not produce a strained enone right away, hoping that this change would relieve the strain induced in our system. After successful cyclization, we could potentially oxidize the allylic alcohol to the ketone, displaying our enone. This strategy in fact proved successful, as we can take our aldehyde and homologate it to the epoxide using dibromomethane and N-butyllithium in a 72% yield. Next, deprotection of both silyl ethers using TBAF and reprotection of the secondary alcohol using TBS chloride gives rise to the intermediate tertiary alcohol in a 56% yield over 2 steps. Next, we can open up the epoxide using magnesium diiodide to reveal the intermediate iodohydrin. In order for cyclization to occur, we had to protect the secondary alcohol as the triethylsilyl ether, and upon treatment with sodium hydride as base, we observed the cyclized product in an excellent yield of 98%. We can selectively deprotect the test group over the TBS group using pyridinium paratoluol sulfonate as a mild acid. A Swern oxidation gives rise to our enone in a 72% yield. Initially, efforts at the final deprotection of the secondary alcohol failed using common reagents. We owe this to the instability and high reactivity of our enone. As such, when subjecting to acetic acid and methanol, we observed readily occurring 1,4 addition of methanol. Finally, a deprotection with aqueous hydrofluoric acid and tetrahydrofuran gave our deprotected enone in an 81% yield. To synthesize our cyclohexanone fragment, we can start out with a nantu-enriched S-norcarvone. We can perform a 1,2 addition of a lithium enolate using cerium trichloride as Lewis acid to give rise to our intermediate allylic alcohol. Upon treatment with pyridinium chlorochromate, we can perform a Babler-Dauben oxidation. Hereby, the intermediate chromate ester undergoes a 3,3 sigmatropic rearrangement to give rise to the corresponding enone. Upon saponification with potassium carbonate and methanol and water, we can display our carboxylic acid. Trying to couple the two fragments via an esterification proved rather difficult as numerous reaction conditions and reagents failed, such as common carbodiamides and various peptide coupling reagents. Even Yamaguchi's reagent, Otera's catalyst, or classic Fischer esterification conditions using acid yielded no product. Going back in search for logic, we asked ourselves why this reaction is failing. One thing we had noticed while deprotecting our allylic alcohol of our enone was the incompatibility of basic reagents. To run a control, we stirred up our enone with different amine bases and found that it decomposed rapidly within minutes. The other problem we had identified was that activating our carboxylic acid with a leaving group, for example as the acyl chloride, as commonly done in esterification strategies, could be problematic due to the alpha-acidic proton. Upon elimination, this pathway could reveal a highly reactive ketene that engages in non-productive side reactions. These two problems we identified, the high sensitivity of our enone to base, and the challenge of finding an appropriate activating reagent, posed a great challenge. We asked ourselves if we could overcome this with a very fast reaction time to avoid the usual esterification conditions that stir for up to an hour in the presence of amine bases, and avoid a long lifetime of the activated carboxylic acid intermediate that seems to be unstable. After tedious experimentation, this led to the design of very specific conditions. Starting with triphenylphosphine oxide, we can activate to the phosphonium salt at 0 degrees using oxalyl chloride. Adding our carboxylic acid, we generate our activated intermediate as the triphenylphosphonium salt. After numerous experiments, we found that the sweet spot of stirring in between -30 and -40 degrees for 10 minutes allows for the acid to react, yet not having the formed product decompose too rapidly. After activation is done, we cool to -78 degrees and add in our alcohol. At these low temperatures, we drip in diisopropyl ethylamine as base to mop up the acid, upon which the ester bond rapidly forms, expelling triphenylphosphine oxide as a fantastic leaving group. Overall, we could successfully optimize this reaction to run it reliably on larger scale and give rise to our ester in a satisfactory 87% yield. With our precursor in hand, we planned on conducting the intramolecular 1,4 addition, but found that upon treatment with various strong or weak bases, the ester proved to be inherently unstable. However, upon treatment with DBU as base and dichloromethane at 0 degrees, we isolated out the following product in a 13% yield, which we could confirm by X-ray crystallography. We were surprised by this unexpected finding and screened different combinations of base and temperature to land at the following procedure to give the pentacycle in an 84% yield. Hereby we heat the starting material to 120 degrees in dimethylformamide under inert atmosphere. We add DBU in one portion with a reaction being done in seconds. Surprised by this reactivity, we asked ourselves how this reaction can proceed mechanistically and came up with the following suggestion. As we take a look at our ester, the proton at C12 can be abstracted, enolizing the vinylogous beta-keto ester. We propose that this intermediate undergoes the planned Michael addition to construct the C11-C12 bond. Hereby, the nucleophilic attack comes from the top face, giving rise to the cis-fused ring system. The tetracyclic intermediate possesses another acidic proton at C12, which can be abstracted in a second enolization event. If we take a closer look, we see that the enolate is in close proximity with our neighboring ketone at C6. This undergoes an aldol reaction to forge the central six-membered ring. Upon isomerization of the double bond, we end up with the enolate at the C12 carbon. Looking at the bowl shape of the left-hand side of the molecule, this enolate will preferentially be protonated from the convex phase, giving rise to our product. This locks in the correct stereochemistry at C12, overall constructing 2 bonds and 4 stereocenters in a single step as one diastereomer. Utilizing this astonishing cascade, we set out to finish the total synthesis. Taking a step back, we can look at the general concept of the synthesis and see the transformations that still have to be done in order to finish the natural product. 1. We have to reduce the tetrasubstituted double bond of the enone. 2. Install some sort of oxygenation at our C5 position to then set up for 3. The semipinnacle ring expansion. Trying to reduce the tetrasubstituted double bond of our enone in a complex setting, we found good reactivity with samarium diiodide as a single electron reductant. However, the product we observed was exclusive 1,2 reduction of our carbonyl group, which we could confirm by NMR. Surprised by this result, we sought out a mechanistic hypothesis. Upon forming the L anion, we realized that the resonance form of the ketyl anion is in a perfect position to abstract the proton of our tertiary alcohol in a 1,5 proton transfer. This would preferentially give our 1,2 reduction product over our desired 1,4 reduction product. This is in alignment with the fact that we only observe 1 epimer at the carbon of our resulting lilic alcohol, indicating that the proton exclusively gets delivered from the back face of the molecule. Aiming for a workaround to this problem, we deemed protection of our tertiary alcohol would shut down the proton transfer and unwanted reactivity. We found that protecting as the triethylsilyl ether gave the best result, and upon treatment with samarium diiodide, we indeed observed no 1,2 reduction, but exclusive 1,4 reduction with subsequent elimination of the silanol. We sought to utilize this product and aimed to install oxygenation at C5 through a convenient allylic oxidation. While initially evaluating conditions, we ran into problems with unwanted reactivity of our isopropenyl group. We thought to potentially isomerize the double bond upon treatment with DBU as base. However, to our surprise, we found that our molecule had undergone a CH oxidation under air. Luckily enough, we figured this out by growing a crystal of our initially isolated product to confirm the unique structure. After careful optimization, we could reliably reproduce this reaction with a 67% yield, being very sensitive to the oxygen atmosphere and stirring rate of the solution. Again, looking at the mechanism, we believe that our molecule has the ability to form a captodative allylic radical upon CH abstraction by a triplet oxygen. Upon radical recombination and deprotonation by DBU, we can reveal the peroxy anion. Similar to a nucleophilic epoxidation sequence of an enone with hydrogen peroxide, we propose that the peroxy anion can add into the beta position of our enone, and then be cleaved to the corresponding epoxide. Upon protonation, we end up with our product. Looking to reductively open the epoxide, we again turn to samarium diiodide. Upon reaction, we found that we could indeed open the epoxide, however the resulting tertiary alcohol rapidly eliminated to give rise to the corresponding enone. We again deemed that hydrogen bonding between the hemiacetal and our tertiary alcohol played an important role in enabling the samarium enolate to rapidly force elimination. We thought to transform the secondary alcohol into a better leaving group, potentially enabling the ring expansion as well as disrupting the aforementioned proton transfer. Hereby we found that forming the acetate with acetic anhydride proved the most reliable, and installation proceeded in an 85% yield. Investigating the reductive epoxide opening on our new substrate, we were faced with the same problem of elimination. However, we could see trace formation of ineleganolide in our crude proton NMR with around a 2% yield. Thrilled about this result, we hope to optimize the formation of our natural product with the semi-pinnacle rearrangement evidently happening in the same pot. Thinking about optimizing this reaction, we drew out the tertiary alkoxide and samarium enolate that we believe to be a viable intermediate upon epoxide ring opening. Aligned with our previous proposal, one possible pathway would be protonation of our alkoxide. Looking at this intermediate, we deemed this pathway to be responsible for subsequent elimination, giving rise to our unwanted side product. If we instead think about protonating the samarium enolate, we would end up with the following intermediate, which looks promising for the semi-pinnacle rearrangement to occur, with the acetate as a viable leaving group. This would lead to the wanted ring expansion and our pathway to ineleganolide. Giving into this mechanistic hypothesis, we would need to find a way to protonate the resulting samarium enolate preferentially over the imminent tertiary alkoxide. Looking at our reaction mixture, we thought to tweak the product formation through adjustment of the pH of our proton source to slow down the fast protonation of our tertiary alkoxide and instead protonate the more basic samarium enolate. After numerous experimentation, we found that addition of an aqueous 1 molar sodium hydroxide solution as high pH proton source yielded the best result in line with our previous proposal. We were thrilled by this result and could obtain ineleganolide in a 45% yield, acquiring an X-ray crystal structure of the final natural product. In summary, we could present an asymmetric convergent total synthesis of the complex nosembronoid diterpenoid ineleganolide. Starting out with 2 enantioenriched fragments, we developed a route to a highly strained bicyclic enone through intermolecular SN2 cyclization. Showcasing unique esterification conditions for highly sensitive substrates, we could couple these 2 fragments together. The subsequent vinylogous beta-keto ester underwent a Michael addition aldol cascade to give rise to a pentacyclic intermediate as 1-diastereomer with exclusive formation of the correct epimer at C12. Upon reduction and then CH oxidation under air, we can showcase a samarium diiodide-induced reductive epoxide opening and semi-pinnacle rearrangement in the same pot to synthesize ineleganolide in only 6 concise steps after union of our 2 fragments. We hope that our total synthesis and the chemistry developed contributes to solving problems in future syntheses of complex molecules of this class and enable further investigation into the bioactivity of the nosembronoid diterpenoids and ineleganolide specifically. With that, I would like to wrap up this episode of the Research Spotlight and give a big thank you to Caltech and the Division of Chemistry and Chemical Engineering where this research was conducted. I would like to thank the Stoltz Group and specifically Professor Brian Stoltz for his ongoing support. Furthermore, I would like to give a big thanks to Dr. Scott Virgil, who runs the Caltech Center for Catalysis and Chemical Synthesis, who has really become a project partner and friend to me during this research project, and working with him has been an absolute pleasure. I would like to acknowledge the previous group members who worked on the old route in pursuit of ineleganolide, and whose published research and results paved the way for this synthesis, specifically alumni Dr. Sejong Han, whose detailed thesis helped out tremendously. Thank you to the Reisman, Fu, and Nelson group here at Caltech, who provide an open, helpful, and collaborative environment to conduct research in. Thank you to the National Institute of Health and the Heritage Principal Investigators Program for generously providing funding to enable this work. I encourage any viewers to reach out in case of any questions or discussions about the research, and thank you for tuning in.
Thank you for joining us for this Research Spotlight episode, and thank you to Benjamin for this interesting talk. If you enjoyed this episode, you can support us by subscribing and telling your peers about this podcast. Feel free to leave a message with questions or comments. Follow us on Twitter to stay up to date, and see you all next time.